Hello again. We're still working away with the formula that I call E equals N delta H and that the notes call delta RH equals N delta RHM. So let's see what we can do with these problems. 1 gram of aluminum reacts with oxygen. This reaction liberates blah. Okay, so we have a reaction that releases a total of 31.10 kilojoules of heat. And 1 gram of aluminum went into that reaction, and they're asking what is the molar heat of reaction for this aluminum, as in what is its delta H. They said molar, so they're talking about this one. And this number is going to be measured in kilojoules per mole of aluminum. So we know the total energy that was released was 31.10 kilojoules equals, they didn't exactly give us the number of moles, but they kind of did. They said we have 1 gram of aluminum, and we can always do mass divided by molar mass to find number of moles. So mass 1 gram divided by molar mass 26.98 equals 1 divided by 2698, 0.037064. That's probably enough. Moles of aluminum would be our N. So that number goes here. 37064 moles of aluminum times a delta H we don't know. How do you get the delta H alone? Divide both sides by 0.037. So 31.10 divided by 0.037064, we get delta H equals 839.089. Units would be kilojoules divided by moles of aluminum. And kilojoules per mole of aluminum is exactly what you'd expect to get for a delta H, so this makes perfect sense. How are we for sig digs? This mass has 4. The enthalpy had 4. 2698 had 4. It looks like we can give 4 in our answers, so 839 point, round up, 1. 839.1 kilojoules per mole of aluminum. And they said, what is the molar heat of reaction for aluminum? This number isn't really complete until you've checked its sign. Is it really supposed to be positive, or is it a negative number? Well, looking at the question, this reaction liberates, as in releases, as in puts out, 31.10 kilojoules of heat. If you release heat like that, then you are exothermic, and that means this number should get a negative sign on it. There are some mathematical ways to tweak this number so to make sure that this comes out with the proper sign on it. I don't think any of them are worth it. I always just check at the end. There's always some detail in the question that will tell you if energy is being released or absorbed. And once you find that, you either put on a negative sign or you don't. That is my advice, which you can take or leave. Okay. These questions are also about finding delta H. And these are for reactions that are already written, and someone has already told us the total energy that comes out of these reactions. So when they give a delta H like this, the trouble with this is it isn't kilojoules per mole yet. We're going to fix it. This says if you use 2 moles of hydrogen and 1 mole of oxygen and you make 2 moles of steam, then you will get 483.6 kilojoules of heat. So if we're talking about hydrogen, the way to think of this is this reaction makes 483.6 kilojoules for every 2 moles of hydrogen you put in. if you divide that out, you get 241.8 kilojoules per mole of hydrogen. And if they're just saying calculate the molar enthalpy, then we should be good about the signs. So I'll carry this. There was a negative on this. I'll put a negative on my finished answer. So when they give a delta H for a reaction, it's for the reaction as written, and they're saying, we don't know which substance you're interested in here, so you can divide this by the moles of any of these guys, and you'll get a molar enthalpy. You can divide by 2 if you're doing hydrogen, divide by 1 if you're doing oxygen, which means you'd get 483.6, or you could divide by 2 and get moles of steam. Not too hard, but let's do a few anyway. This one, they're talking about the thing that reacts with oxygen being the ammonia. So in this case, we're getting 1,134.4 kilojoules for every 4 moles of NH3. 1134.4 divided by 4 is 283.6 kilojoules per mole of ammonia. And this should be negative. Do you see why? In this one, instead of delta H, they wrote the heat in the reaction, and they wrote it on the right side, meaning it's being released. That tells us exothermic, meaning we get to put in a negative there. Next one, the thing reacting with oxygen will be nitrogen. So in this one, we're using 163.2 kilojoules for every 2 moles of nitrogen. Divide that and you get 81.6 kilojoules per mole of nitrogen. And should this be negative? No, because here the heat's being used. It's on the left side. It's an ingredient. You must put in heat to drive this reaction, so this reaction's endothermic. Its delta H should be positive. And last one, iron plus oxygen makes an iron oxide. Here we're getting 1,118.4 kilojoules for every 3 moles of iron. 1118.4 divided by 3 is 372.8 kilojoules per mole of iron. And should this be negative? Yep, there's a negative here. We divided by 3, so this reaction is exothermic. It gets a negative there. So this is another ugly place with the notation where we use delta H to mean kind of 2 different things. This is the delta H for an entire reaction. It's not a molar enthalpy until you've divided it by moles of something. Sometimes that means dividing by 1, and the math is kind of pointless or easy, but get used to always doing this step, please, and it'll keep you from using a number in the wrong place. Because if you forget to divide by a 2 or a 4 or a 3, you will run into trouble very quickly. Fair enough?